Hello everyone, this is Richard again. I wanted to explain a little bit more about going from a velocity graph to a position graph. Now in the last two videos we used this very simplified example here. But you might have been saying to yourself, Richard, this is really quite an idealized situation. Never in real life would you be going exactly 60 miles per hour for 1 hour, then instantaneously go to 120 miles per hour for another hour, and then instantaneously go to 30 miles per hour for that last half hour. In reality, we know that velocities are continuous and changing all the time. We know this through experiences in riding with our car, or riding in our car. We know that we change our velocity, we speed up and we slow down, and those changes are not instantaneous. For example, let me give some example data over here, where not specifying values yet, but maybe we have some velocity versus time graph that looks like this, where really at no point in the whole motion is the car ever technically going at a constant rate. Maybe you could say it's going at a constant rate up here or here, but if it does so, it doesn't do so for long. So if we wanted to ask the question of how far the car went in this scenario, or scenarios like it, how exactly would we do that? Because we've only done it for the case in which we have nice, constant values of velocities so that we can make these rectangles here. And of course, just do the calculation which we did before, where we just did the velocity times the time. If we come over to this situation over here, we wanted to do velocity times time, we would be faced with the question of what exact velocity do we use? Do we use that velocity, or this velocity, or this velocity, or even this velocity? Furthermore, if we even had the velocities at those points, what time would we even multiply it by? Because once you get to this point over here, the velocity is now changed. So we're left with the question of how exactly we deal with this situation. And that's what we're going to do in this video. So let's go ahead and specify a more realistic situation. Again, if we were in real life, and you've seen this with your vernier analysis carts, in reality, you never have this nice smooth curve. What you have are individual measurements of the velocity. So really, this is an idealized situation to where maybe this is representing the true velocity, but the data we have, we might only have the velocity at the beginning, at this point, at that point, at that point, and at points along this at evenly spaced intervals, or just any interval in general. So with this data, how would we go to a velocity versus time graph? Or how would we go from velocity versus time to position versus time? So let's think about how we might do this. Well, we might imagine that, it'd be, we don't really know exactly how to do this. We don't know how to get an exact answer. But what we do know how to do is this rectangle thing. So, just for sake of being able to do something, let's think if we can apply the rectangle thing over here. So let's say maybe this data point where it starts out is 30 miles per hour, and maybe this data point here is 40 miles per hour, and that's t equals 0, but at this time of 40 miles per hour, perhaps this is half an hour which has passed. So, if we say that the car starts at 0, well, of course, and this is position versus time. We say the car starts at 0, that's the first data point at 0. But we want to ask how far the car has gone in half an hour. Well, okay, we have a time, but what velocity do we use? Do we use that velocity or that velocity? Well, let's think about it. If we use this velocity here and multiplied that by half an hour, we would basically be saying that the car went 40 miles per hour for that whole half hour. And that's of course not true. 40 miles was, or 40 miles per hour was how fast, was how fast it was going at its max speed. So we would be overestimating how far the car went. In a similar way, if we use 30 miles per hour and multiplied that by half an hour, well, that would be undershooting now, because we know in this interval the minimum speed was 30 miles per hour. So let's maybe compromise here. What if we use the average of 40 miles per hour and 30 miles per hour? Which, of course, would be 35 miles per hour. And so, if we made a little rectangle here at 35 miles per hour, it's a good midpoint. It's a good estimate. Now, the estimate won't be perfect, but it will be pretty close, and then it'll be at least something that we can deal with here. And I'm going to move these values around so I can write more later. But remembering back to that area under the curve video, if we wanted to do it perfectly, we would have to perfectly get this area and this shaded region here. But of course, as we know, we can't really do that. So what we're going to do is we're going to be approximating this area here. And we're going to call the height of this rectangle, we're going to call it the average of 30 and 40, which of course is just 35. So then what we're going to do is we're going to approximate the distance the cars went in this half hour by the following calculation. It'll be 40 miles per hour plus 35 miles per hour divided by 2. This is to get the average. And then I multiply that by 1 hour. Oh, sorry, this was 30. I was getting ahead of myself. 30 miles per hour. And that's for a half hour. And we do this calculation. So, of course, this is 35 miles. Well, I'll do it sequentially here. This is 35 miles per hour times a half hour. And that would be 17.5 miles. So, and of course this is an approximation, but we say that after a half hour, the car has gone approximately 17.5 miles. And while that won't be perfect, it'll be pretty close, and it's certainly better than nothing. Well, let's continue this example. Let's say we have this other data point here, so that's for half an hour at there. But let's say the data point here, this is a 1 hour of total travel time. So we measure after 1 hour of travel time, the car is at 50 miles per hour. And now we want to ask, after that 1 hour how far the car has gone in total. Well, it's good that we know how far the car is at after half an hour of travel. So we just need, in this half an hour interval, we need to calculate how far the car has gone in that interval. And the way we do that is multiplying this half an hour interval by how fast the car was going. But we again run into the same issue. Which velocity do we use? Because it's continuously changing throughout the entire motion. Well, we solve it in the exact same way, is that we use an average of both the points, as treating that as though the car were moving at that average velocity over the entire half an hour. Or yeah, over just this little half an hour. So I do that calculation. So it would be 50 miles per hour plus 45 miles per, wait, 40 miles per hour divided by 2, get the average, and then we multiply that by the time, which is, of course, half an hour. But I'm going to write this in a way, I'm going to actually write out the full calculation. Implicitly in my head, I'm doing this. I'm doing 1 hour minus half an hour, because I want this little time span here. Because what I'm concerned about is how far the car has gone in that little time span. Because once I get that number, I'm going to add it on to this number down here to get how far the cars went in total. So this is how far the cars went in this half an hour time span, and that gives me 22.5 miles. So in this half an hour time span, the car has gone an additional 22.5 miles. So if I want how far the car has gone after an hour in total, I need to add this number here, the 22.5 to the 17.5, to get out a value of 40 miles. And of course, if we say, for example, perhaps the car at this time interval has dropped back down to 40 miles per hour, and that looks kind of like a large distance, and I call this 2 hours. We do the exact same thing again. How far has the car gone after 2 hours? Well, I need how far it's gone in that time interval. This is clearly one total hour. Which velocity do I use? Well, we do the exact same thing again as taking the average. Clearly, I just did this. The average of 40 and 50 is 45. I'll even write it out again, just for being as clear as I possibly can. Take the average, and the total time would be 2 hours minus 1 hour, and that would be 45 miles. Goodness gracious. 45 miles per hour times 1 hour equals 45 miles. Now, if I want how far the car has gone after 2 hours, I add the 45 miles per hour, the 45 miles to the 40 miles, because the 45 miles is how far I have gone in this time span, and I started at 40 miles. So clearly what I would do is add the 45 to the 40 and obtained for myself 85 miles. And to say, I think at this point I don't need to do another one. But you can see here the process. If you have these data points, and also I can draw the triangles out a little bit more, like that, something like that. But you can see the process here basically is almost exactly what we did over here, except we're now faced with the issue of, over here we had a nice constant velocity. It was clear which velocity we used to multiply times time. Over here it's not clear. So what we do is we just take an average of 2 data points to sort of split the difference of maybe that data point and that data point, and that would be the velocity that we used. We multiply that by time, and we get our distance traveled. And you could see I could keep doing this process for all these data points. It doesn't matter how many data points you have. You can keep doing this, and you could keep building up your position data. And that is how you would go from some arbitrary some arbitrary velocity data to position data.